My name's Tom Secord. I work with Carollo Engineers. I'm the chief desalination technologist. My role in PFAS, certainly RO removes PFAS, but we can also use it to concentrate the PFAS, and that's particularly important when you're dealing with some of these destruct technologies. I grew up in New York State. I lived on the banks of the Hudson River. When I was a kid back in the 70s and 80s, the issues were PCBs in the Hudson River. Today, as we look at New York waters, the issues are, the next round of manufacturing that's coming in. Those manufacturers are potentially generating PFAS. So, learning the lessons from the past, it's important for us here in New York to, think forward. It's like, how can we prevent that issue on the Hudson River from happening again? So I'm gonna give everybody that's speaking here a chance to introduce themselves rather than reading from bios. I'm gonna pass the microphone around. And then, we've got about 15 minutes per presenter. That's going to take us right up to the time limit unless somebody's quick. But I would like to, if you're all willing, stick around and do some Q&A. So if you're up for that, we're all going to end up in the lunch line anyway. So we'll end definitely at noon. So okay. Rosa.
Thank you, Tom. Hi, everyone. I'm Rosa Yu. I'm with Carollo Engineers. I'm Carollo's national PFAS lead. My focus is mainly managing PFAS and addressing PFAS contamination in all sorts of water matrices, from drinking water, groundwater, surface water to wastewater. Landfill leachates, all sorts of matrices. And I'm very excited here to learn about all those destructive technologies today from all the different vendors so that we can close the PFAS contamination loop in the water cycle.
Good morning, everybody. My name is Eric Drugach with Revive Environmental. I serve on the business development team here at Revive. My background is in emerging contaminant treatment and water treatment. And since joining Revive, spent the last couple of years working on primarily AFFF remediation projects, groundwater, and landfill leachate treatment.
Good morning, everyone. My name is Sarah Meyer. I'm with Inspired Solutions. I'm actually pretty familiar with Syracuse. At one time, I worked with O'Brien and Gear engineers that were here. I spent about 25 years in research and consulting and remediation of waterways, and came to Inspired Solutions in 2022. And we have a PFAS destruction technology, obviously, for water-based matrices, and I'll tell you more about it today. I'm really glad to be here.
Good morning, everyone. Tom Holson. I'm here representing DMAX Plasma. I'm also a faculty member at Clarkson University in civil and environmental engineering. I'll talk a bit more myself and the leadership team when my talk starts.
Thanks. Hi, everybody. I'm John Tracy. I'm with the company Clarity, who is also a PFAS destruction technology firm. Proud Clarkson alumni, undergrad. And let's see, I've worked a lot in the water space, previously in the semiconductor space. We do some work with semiconductor, other industrial manufacturing. I'll get into all this more when we give a little introductory presentation.
And good morning, everybody. My name is Salman Mujovic. I'm the CEO of Purified. We make plasma-based treatment technologies and analytical tools. Happy to be here with other destruction-based technologies. I think one thing that's very important here is, I know it's seems like we're all competitors, but we actually all need to push this sustainable approach forward. If we keep using the word destruction, really what we're trying to say is that it's sustainable. So excited to see what everybody else is working on and kind of push this forward together.
We're going to start off with Rosa Yu, who's going to give just some general background on PFAS so that the presenters can focus more on their destruct technologies.
Thanks, Tom. So PFAS treatment and destruction for New York State waters. I'm going to start my presentation by saying PFAS is a one water problem. As you know, due to the chemical persistency and biological persistency of PFAS as a class of chemicals, they are pretty labile and they are pretty prevalent in our water cycle. So PFAS not only pass through drinking water treatment utilities, wastewater treatment utilities, but also end up being our landfill leachate, and also other industrial effluents. So it's not a single point of source that you can control PFAS without considering the entire water cycle. So PFAS occurrence in the New York State. So this is showing the UCMR5 sampling results for drinking water sources. So this graph or this analysis includes UCMR5 data as of December 2024. So far, there were 253 water systems have been sampled in the New York State, and 31 utilities have been identified with PFAS exceedance. So that's 12.3% New York State drinking water utilities have at least one sample exceeding the PFAS MCLs. So in terms of the public health implications, that's about 2 million consumers being affected by the presence of PFAS in their drinking water sources. And due to this, based on the statistics, there's about 8.5% groundwater entry point samples had PFOA exceedance of over 4 nanograms per liter, and surface water entry points are less impacted, but that's account for 3.7% of surface water entry point samples have PFOA exceeding 4 nanograms per liter. So last week, EPA announced the new the revision to the National Primary Drinking Water Rule for PFAS. So one thing I want to highlight over here is even though less PFAS will proposed to be regulated, EPA is releasing or is considering or reconsidering resigning the MCLs and hazard index approach for PFBS, PFHX, GenX, and PFNA. But the treatment focus is probably going to be unchanged because in the state of New York State, PFOA is the driving PFAS in terms of PFAS treatment technology selection as well as performance. So as you can see, PFOA is the most detected regulated PFAS, second to PFPEA and PFHXA, whereas PFOS, PFHXS, PFBS, and PFNA are barely detected. So New York State Department of Environmental Conservation, DEC, has released draft guidance to discharge of PFAS discharges of PFOA and PFOS. So those guidance level, even though it's not regulating PFAS in the surface water discharges, but it does provide the state with some health information of PFOA and PFOS. So the state may take additional actions or efforts to regulate PFOA and PFOS if deemed necessary to protect surface water sources. And the human health guidance level for PFOA was 6.7 nanograms per liter, whereas PFOS is 2.7 nanograms per liter. So those are relatively pretty low those are pretty low guidance levels when it comes to health impacts. And especially for PFOS, it's even lower than the drinking water MCL for PFOS. So when it comes to PFAS treatment, you probably all have heard of the best treatment technologies, including GAC, ion exchange, or novel adsorbents, or high pressure membrane like nanofiltration or reverse osmosis, or some more novel process like foam fractionation. The nature of all those treatment processes is they don't destroy PFAS, they only concentrate PFAS. So it's either using the process as a standalone process, such as GAC ion exchange, or a combination of those, such as nanofiltration or reverse osmosis combined with foam fractionation. You will end up with a residual stream that's more concentrated in PFAS that needs to be taken care of or properly disposed of. So increasing limitations on water wastewater treatment residual disposal require PFAS destruction. So we know, for instance, GAC ion exchange treatment or novel adsorbent treatment, PFAS are getting concentrated on the solid media. So you will generate spent media as your treatment residual. And GAC can be reactivated and potentially reused, whereas ion exchange or novel adsorbents, they're typically sent for incineration to end the PFAS cycling. For liquid concentrates like RO concentrate, nanofiltration concentrate, or foamate or foam fractionation residual, typically if the community is on the coastal lines, then ocean discharge can be an option. But here in New York State, that's typically not an option. Deep well injection, sanitary sewer disposal, surface water discharge, those are typical liquid concentrate discharge or disposal approaches. But the looming issue is, if the utilities or if the owners cannot easily discharge the RO concentrate or the foam, then how to address PFAS. In terms of wastewater treatment residuals, biosolids, I think everybody knows there's lots of attention in terms of the health impact and also the risk assessment when it comes to PFAS in biosolids. Typically, biosolids can be land applied and reclaimed. Surface disposal, incineration, landfilling are also alternative approaches. But due to the presence of PFAS in biosolids, landfilling and some states are taking actions to rule out landfilling of or land application of biosolids that limits the biosolids disposal pathways. So in terms of regulatory framework, so even though PFAS haven't been classified as hazardous compounds under RCRA, but if they do in the future, the residuals such as spent media or oral concentrate generated from PFAS treatment facilities will need to be sent to RCRA Subtitle C permitted treatment, storage, and disposal facilities. This just means for owners treating PFAS, it will increase the cost in terms of residual disposal and management. For NDPES, EPA actually has issued human health water criteria for PFOA, PFAS, PFBS December last year. So those are recommendations provided to states and tribes to derive water quality standards for water bodies under the Clean Water Act. Even though they're not regulated yet, but those really low health criteria, just like the guidance levels established here in the New York State, may inform PFOA, PFAS discharge limits for surface water. And for biosolids, EPA has released the draft sewage sludge risk assessment for PFOA and PFAS. And as I mentioned earlier, the presence or the detection of PFAS in biosolids, some states are ruling out their land application possibilities. So with all that being in mind, due to the evolving regulatory framework for PFOA, PFAS, and PFAS in general in waste in waste residuals or in wastewater treatment residuals, PFAS destruction becomes a necessity. So the rise of PFAS destructive technologies, there's lots of emerging technologies these days when it comes to PFAS destruction, and they can be fit into those main categories. And we will hear today from some of the technology providers in terms of what each technology is about. So from the big category point, thermal treatment, hydrothermal treatment, electrochemical oxidation, advanced reduction, senolysis are the mainstream destructive technologies or processes for PFAS. So today we will hear from Revive talking about supercritical water oxidation, which fits into the hydrothermal treatment category, and then electrochemical oxidation, Clarity, and non-thermal plasma, which we will have purified in DMAX, and also photoactive defluorination process or UV advanced reduction process from Inspired Solutions. So hopefully today we will learn more about each technology and what they do when it comes to PFAS destruction. So why PFAS destruction is a challenge? Because the carbon fluorine bound is one of the most energy intensive bonds when it comes to organic chemistry. So to break the carbon fluorine bound, it takes about 485 kilojoules per mole energy. So that's the reason why it's very energy intensive. So as a reference, you can see typical hydroxyl radical, which we consider as advanced oxidation processes. They provide 270 kilojoules per mole. That's still not enough energy to break the carbon fluorine bound. Sulfate radical, which can be generated using a UV-based or plasma-based process. And as you can see, those energy are still not sufficient to break the carbon fluorine bound. So that's the reason why PFAS destruction is energy intensive or can be challenging. So most destructive technologies, therefore, require intense energy. I would say there are innovations and there are breakthroughs when it comes to those technology development to lower the energy cost for PFAS destruction, which we will hear about, and also long reaction time, because you need to supply sufficient energy for the carbon fluorine bound to break. So why reaction time matters? Because it relates to scalability from an engineering perspective, and also it determines the configuration. You know, if long time reaction time or exposure time is required, then we are discussing the differences between batch treatment, semi-batch treatment, or continuous flow treatment. So when it comes to destructive technology evaluation, hopefully those are the four matrices or the four sections of criteria that we consider. So first, starting with matrix. So what does each technology treat, right? So it can go from liquid concentrate to solid concentrate. So from landfill leachate, industrial effluent, AFFF, oral concentrate, foamate, to more solid waste such as sewage sludge or spent adsorbents. So as I mentioned earlier, scalability is definitely a consideration, especially for large scale applications. So, you know, hopefully we will learn from all the technology providers in terms of their current capacity and their integration with additional concentration processes such as RO or such as foam fractionation or novel adsorbent, that you do the additional concentration step to increase the PFAS concentration in the waste stream. Flow capacity, as I mentioned earlier, is it, you know, batch treatment, semi-batch treatment, or continuous flow treatment? Modularity, as I mentioned earlier, reaction time is a critical consideration when it comes to PFAS destruction. So can you increase the system capacity or throughput by providing multiple modular systems and system configuration? So you will also hear today from those technology providers in terms of TRL, or technology readiness level. So those are NASA developed criteria when it comes to an innovative or new technology. So hopefully we will learn about when the technology is whether or not the technology is market ready, and what are the gaps. Challenges and breakthroughs. So as I mentioned earlier, PFAS destruction is a energy intensive process in general. So there are innovations, there are technology breakthroughs that has been conducted, or research has been conducted to narrow that gap. So for instance, reactor geometry, we can improve the reactor geometry, for instance, for non-thermal plasma to increase the energy efficiency and radical generation when it comes to PFAS destruction. Matrix effect. All those residual concentrates or those residual streams are pretty complex, not in terms of PFAS concentrations, but also in terms of its matrix, right? Some matrix can be very rich in organics like landfill leachate, and also some can be very salty like RO concentrate. So how can you overcome those matrix effect whereas effectively treat for PFAS? That's another major consideration. And also complete defluorination, right? We know PFAS not only can form, but also can transform when doing the destructive process. So complete defluorination is always a major consideration when it comes to the treatment performance or the destructive performance when it comes to PFAS. So with that, I'm gonna hand it over to each of the technology providers.
So first up, John.
All right, thank you, Tom. Thank you, Rosa. So I'm going to, in this presentation, I think, answer some of the questions that Rosa raised in her four quadrant diagram that was just shown there. So just a quick one slide overview of Aclarity. We were formed out of UMass Amherst back in 2017. We're a small team, 15 or so of us based in Southeast Massachusetts, and really have been 95% focused on PFAS remediation since about 2020. The company was originally formed to deal with various kinds of recalcitrant COD, tough to break down organics and wastewater. So TRL level, we see ourselves at TRL level 8 or 9. We've put multiple pilot versions of our full-scale technology out into the field, and we'll show you a full-scale system that we've developed and deployed this past year. Basically, we're a startup. We're running off of seed money and Series A money to pay the bills and to help us develop into a solution provider in this industry space. So a different 4-block diagram. This helps to give an overview of the different types of technologies in the PFAS treatment landscape. We, and most everyone here who's going to be talking, are in the destruction space. In the bottom right, Aclarity is focused on electrochemical oxidation. So using DC power and electrodes to basically take electrons off of the PFAS compounds that we treat and break down PFAS with an electrochemical process. We work very well behind certain pre-concentration technologies, such as foam fractionation or different forms of membrane technology that can reject PFAS, put it in a concentrate stream that we can then do our work on. The capture and disposal technologies in the upper left, they're very helpful really downstream of our process if we want to treat and then directly discharge streams to the environment. Economically, we run best when we're doing about 99.5 or 3 nines worth of destruction of PFAS. To hit very low limits, like what Rosa was showing in her slides, we'll want to run through a polishing ion exchange or GAC or something after our process. We also can work with regenerable resins and do treatment of the regen wastewater that would be generated from those. And then finally, we're all beholden to the abilities to measure and monitor PFAS in the projects that we're running. Right now, today, pretty much to quantify PFAS or to look at individual compounds, you've got to go to third-party labs, or if you're lucky enough to be doing a project where there is LC-MS, liquid chromatography, mass spec, on site, then great, you can have faster turnaround. We're all kind of starting to look at the emerging fast turnaround total PFAS analysis methods that are just starting to come out into the world today. So a little bit on the background of how the electrochemical oxidation works. What we're doing is direct electron transfer is at the heart of how the technology breaks down PFAS. The anode of cathode-anode pairs in our reactors are wanting to pull, they want to do this direct electron transfer and convert PFAS compounds into a PFAS radical. Once this is done and we begin the breakdown of the compound that way, then the other oxidants like hydroxyl radical and things like that that we generate with these electrodes, together with more of that electron transfer, is what's breaking down the compound. The byproducts, if we're doing our job properly, are fluoride ions in the water at pretty low concentrations, and then carbon-based compounds such as CO2 or carbonates or bicarbonates that would be the breakdown product from the carbon side of the compound. So we do also break down a number of other recalcitrant organics as we're running the process. You can see in the beaker study down below, we're transferring landfill leachate with its dark color and very pungent odor into lighter and lighter waters, I guess, as we're treating the stream and breaking down the organics, breaking down the things that contribute to odor, and doing the treatment process on the leachate. So how do we differentiate ourselves? We're not doing capture for offsite disposal, such as what the media are doing, although that can be helpful as part of a process flow. The concentration steps like foam fractionation or membrane processes, they're complementary to us, right? Our economics are best when we're treating a sample that is maybe millions of nanograms of PFAS in a wastewater stream, instead of trying to attack a large stream like a MGD level discharge from a municipal wastewater plant with maybe 500 PPT or 500 nanograms of total PFAS. We like concentrated streams, lower volume, much higher levels of PFAS. And then, of course, we're part of this category with numbers of other destruction technologies. Supercritical water oxidation, my colleague will talk about that later. They're taking on streams that are very, very highly contaminated with PFAS, like the 3% concentrated AFFF or biosolids or spent media, things like that. That's beyond the upper limits of what electrochemical oxidation can do. Our upper limit really is like a good, strong foam fractionation concentrate or the regeneration wastewater from regenerable specialty resin that's doing PFAS capture. Those are things we work with well at the upper end. At the lower end, we're looking at 5,000, 10,000 nanograms in an industrial wastewater discharge. That's the lower end of what we would take on. I've heard very good things about the UV catalyzed technologies. It'll be exciting to learn more about that, and then also the plasma technologies that are in this space. So what we've developed over time, the company started with small lab scale systems with, you can see kind of, I'm not going to use the pointer because I'll screw it up somehow. The left-hand picture, there's a single electrode in a flow-through cell that we run lab-scale tests on. We do that still today. That's usually the first step in working with a customer and describing how the technology works. Second, we've got a small fleet of pilot systems that have one of the commercial scale reactors that we've developed. 10 of those electrodes from the lab scale system in one reactor, and then similarly a flow-through cell that we can run maybe 50 gallons or so a day. If we're running a high concentrate stream in batch mode, we can do that with this trailer system. And then on the right is a larger commercial system, 8 of those reactors in running in series in a large recirculation loop and pumping scheme. That system, if we're doing a low concentration stream, we can do about 30,000 gallons a day. For very concentrated streams that we want to run in batch mode, we can run maybe 8 or 12 hours on a 250 gallons at maybe 5 million or 10 million nanograms of total PFAS. It's perfect size for treating, let's say, landfill leachate from a 50,000 gallon a day landfill producing that much leachate, running through foam frac, concentrating the leachate by about 500 or 1,000 times, and we're getting between 50 and 100 gallons total per day of leachate to be treated. We'll run that through our systems very well. Okay, so it wouldn't be right if we didn't show some kind of destruction data. So this is, we call it an industrial effluent. It is PFAS that is in chrome plating rinse water. The chrome-based electroplaters or anodizers are using a mist suppressant to keep the chrome, the hexavalent chrome mist from floating around in their plating operations, floating around the building and causing problems with operators at those sites. This mist suppressant contains, guess what, PFAS. And it ends up in the rinse water at the end of the process. It ends up in the baths, but the baths don't get replaced really at all. They just make them up with chemical over time if they need to, but that rinse water is a problem. What we can do is go upstream of the general waste leaving a metals finishing facility, go to the part of the facility that's running these mist suppressants and treat that rinse water directly. So what we're doing is finding a stream that's about 15,000 nanograms of total, or what we call target PFAS. I'll get to that in a minute. Mostly in these mist suppressants, it's this fluorotelmer, this 6,2-FTS. And you can see it in the graph by species below. It's by far, it's about 15,000 of the total of the PFAS that's in the stream. So what we're doing here is we're running a process. I believe this was 6 hours in the testing that we did. We're destroying 98% of the total PFAS. What we call the PFAS-6 is a subset of compounds that includes this 6,2-FTS, includes PFOA, PFOS, PFNA. We're breaking down, 91% or so of those compounds, mainly based on the FTS destruction that we're doing. So in the case like this, we would run this process probably for a little longer time to get a slightly better 6,2-FTS destruction, and then probably the discharge would go through an ion exchange media or a GAC or something afterwards. But this gives you an indication of the types of destruction we're doing, the levels of destruction. So just a picture of what that treatment pilot system looks like. And then I'll conclude, right? We'll answer some of Rosa's questions at the end. The TRL level I talked about, the types of streams we like to handle, concentrated, difficult streams such as landfill leachate, other industrial effluents. And then our company is set to work with engineering firms, with direct end users, and help put together projects in the PFAS space.
Selman.
Thank you. So since we have another plasma technology here, I'll go a little bit into kind of just like how plasma works in general, and then we'll talk specifically about what we think makes Purified special. And so in general, I'll just touch on like where we think plasma could fit into these existing treatment trains. So everybody knows the problem. We'll touch on the solution briefly, specifically our approach, and then some of the experiments, and just touch on a little data, and then where we think some of our next work looks to go. So everybody knows the problem. There's separation. We have to do something about it. The way, as Rosa touched on it, the way I like to look at it is really there's two branches. There's your thermal side and your non-thermal side. All these different technologies have their benefits and limitations, you know, so we're talking cost, resource recovery. At the end of the day, all these technologies suffer from dealing with the scavenging capacity of the matrix, pretty much all the other crap that's in the water that is interfering with your ability to destroy PFAS. And so we like to use a metric known as energy efficiency per order, where it's pretty much a measure of how much energy you need to clean a certain volume of water at 90% removal for a given compound. So in this case, I've collected a few data points for specifically PFOA from different treatment technologies. So as you could see, incineration is very energy intensive. HALT is less energy, but still on the higher side. And then electrochemical oxidation. But the reason why we like plasma is that you can find it to be extremely energy efficient. And so what exactly is plasma, right? A lot of people don't realize that ozone and UV technologies are plasma-based technologies, right? You are making a radical that ultimately you're using to destroy things. So in the case of UV, you're making plasma inside of your bulb, and then you're shooting it out, and only the UV is escaping, right? Now there's new technologies like LED, but I won't get into that. So, however, ozone and UV do not take advantage of the short-lived radicals, right? And so what's nice is that when you make direct contact of plasma with water, you get enhanced reduction in oxidation that takes place. And so how exactly does it work, right? So I'm just, you have a few molecules here I'm just showing you. In the bottom right there is your contaminant of emerging concern that sits in some water, and then you have some gas. So I'm just showing you oxygen and water, but you could have nitrogen, argon, all these different things, right? But in air, there's always this free electron that's hanging out. So when you apply voltage, this electron will accelerate across the gap, right? And this electric field then carries your electron, but hopefully you pump in enough energy into the system that as this electron collides with these molecules, it'll ultimately create radicals, right? And so your oxygen will break up into atomic oxygen, singlet oxygen, superoxide, all these other things, right? And you also make UV in the process as well. So this happens in both in the air and in the liquid. And as it continues to do that, these radicals will react with one another, and ultimately they will continue to react and diffuse into the water. So the way I like to view this is just a cascade of an avalanche, right? And so as a physicist, I view all chemistry in terms of just electrons. So if you can manipulate the electron to give you the energies that you want, you can ultimately induce whatever reaction you want. Right? And so as these things continue to react and diffuse, they'll cascade and ultimately find your emerging contaminant until, assuming you hit it enough times, it should turn into carbon dioxide and water and any inorganic salts. In the case of PFAS, it should be fluoride. And once you turn off the plasma, you'll just be left with the longer-lived species, right? So what makes us special? A lot of people will tell you, that they think they know what's happening in the water. Most of us don't. We like to treat it like a black box, and we'll destroy things and measure things outside or after treatment and try to induce what's happening here. But really what happens is that when you see plasma, right, when you see lightning in air, it's very filamentary, very small, and a very small contact area, right? So the name of the game is how can I increase this contact area? And so how do we get more plasma on water using the same amount of power? In our case, we like to manipulate the geometry. So that ultimately gave birth to what we call the plasma water reactor, or PWR, which is an homage to my nuclear engineering background. And so the name of the game is how do I get the plasma to interact with more water, right? And so here I just have some water droplets I'm showing you, and if these things are closely spaced enough, as I pump more and more energy into this thing, the plasma will continue to propagate across all these different surfaces until you finally have something that looks like this, right? And so when I was a graduate student, which I think many of you in this audience were or are, I thought I could change the world on my first shot. So I made a reactor that could clean 15 gallons a minute. only to realize that it was not cleaning 15 gallons a minute. So we ended up shrinking this thing, and that's what you see on the right here, this GIF that's playing on loop. And that thing was about a few inches tall, like 1 inch in diameter, and recirculating some water. And so what we do is, the thing is that everybody's water is unique. So we have to take your matrix, we then modify the operating conditions and vary all of these different flow and geometry settings to ultimately determine how to optimally treat your water. So everybody will come to you and say, hey, I want this cleaned as quickly as possible. I don't care how much energy it takes. That's one end of the spectrum. Or on the other end, okay, I have this vat of concentrate that doesn't really need to go anywhere, but I ultimately need to get rid of it. Use the least amount of money, aka energy, to destroy it. So that's on the other end of the spectrum. So we like to play around with these operating conditions to kind of map this out and determine what these costs look like. And so we'll operate first in batch mode, sample at various treatment times, and then we monitor the plasma and the water quality real time. And then we've developed in-house analytical methods for PFAS and other emerging contaminants. We used to do our work mostly on 1,4-dioxane and then transition to PFAS. And then we would ultimately design and deploy the pilot. So we're at probably a technology readiness level of a 6. We're in the process of deploying our first few pilots. And we've worked with different state agencies, engineering consultancies, and environmental organizations. But we've tried a wide range of matrices. We've done everything from drinking water all the way up to RO concentrate of landfill leachate and everything in between. One of the hardest things for us is actually that the plasma works in all of these matrices. So the hard part is figuring out, which one should we target first and deploy our pilots in. And so I have some data here. We don't need to really go into it too much. I'd be happy to discuss this on the side, but this is just to show you some of these matrices. So we were given some matrices where electrochemical oxidation was ineffective, specifically this remediation site in groundwater and the RO concentrate of landfill leachate. And this was, a few years ago, so I know Clarity has moved past that, but we've kind of looked for matrices that other technologies struggle in, right? And so what we find is that the plasma will work effectively and very energy efficiently. One big takeaway here is, if you look on the right-hand side, is that you would think that the higher concentration water is more energy efficient to clean, but what we find is that sometimes that's not always the case, right? So in the case of the drinking water, you could see some of these energy efficiencies per order are roughly in similar range of energies used. And so it goes to show that you really need to try it for each matrix before you can kind of say one isn't effective. But that said, you want to focus on higher concentration streams because those are typically lower flow rates. And so I'm just going to show you a quick example of some of the data. And so what we'll do is, this is from Michener Plating site in Michigan. So you look at PFOS, destroyed, right? We vary around some of these different settings. I fit a curve to show you first order decay. And you'll see that this reaction rate is a lot higher than, say, a peaches, which has like an aromatic ring in it, right? So just to show that based on the structure of the molecule, it's harder to destroy. Another big thing is that the shorter the chain, the harder it is too. So they'll go to show here as well, right? And then last but not least, though, what we realized, and this data is several years old, when we first were just trying to figure out what's happening, we'll see that some of these concentrations actually will increase, right? And so what's very important here is that you do need to determine what are the precursors, right? Or how you're transforming some of these molecules into some of things. And as Rosa mentioned, PFOA is the main compound that we're using as our criteria, right? So I want to make sure that I see this peak increase and then ultimately decrease away, which we've seen before. And so the main thing is that longer chains are easier to destroy than short chains, and optimization is critical. So those energy efficiencies per order could vary significant orders of magnitude. And another, just to hit a nail on the head, is that the most cost-effective matrix is not always what you think it is. So similarly with that RO concentrate, we found that the drinking water from Orange County, for example, had similar EEOs, right? In that example I showed you there, that was a different drinking water. And so another major thing to take away is that the kinetics can unexpectedly exhibit non-first order decay, right? So that's when we know that definitely precursors and scavengers play a role in your destruction. And then so what we're trying to really do is figure out, is there a way to real-time measure species and water quality that ultimately serve as surrogates? So instead of always measuring for PFAS and using those expensive analytical tools, even though we've developed those in-house for fast turnaround times, can we ultimately say, hey, I found this surrogate that I can measure on the side and show that it has sufficient destruction? This is something similarly we're modeling with, like, for example, in California, they do indirect potable reuse. They'll use 1,4-dioxane as their contaminant of concern that they use as an indicator. And so they'll use things like pH and total organic carbon to indicate, okay, this is how much how many scavengers I have in the water and how much I should compensate for the destruction. So then I don't have to always directly measure for the PFAS. So, you know, we have several pending studies. We're looking at bench scale, surface water, wastewater, you name it. And then we're deploying these pilot studies in industry impacted groundwater and leachate. And so, you know, some of the applications we're looking at is figuring out kind of the synergy in these advanced treatment trains. So what we're finding is that, you know, you can enhance electrocoagulation, biodegradation, inactivation, and potentially replace some of the treatment technologies that are already in your treatment train. So it would be nice to figure out how we can simplify these processes and then ultimately real-time monitor and dynamically treat the water. And that's the nice thing about plasma. We can vary these operating conditions real time. So if you have an upstream event that takes place like a spill, then we can real time adapt to it if you see some changes in TOC, for example, and say, hey, let me crank up the juice to compensate. And so I'm just going to show you a few treatment trains where we think we can apply this thing. So for example, in GAC-based treatment trains, you know, the spent media, well, you can replace the UV, right? And so in GAC, for example, the shorter chain PFAS make it through, so that's something plasma can be used to destroy, or other trace organics like that 1,4-dioxane that destroys things. And also get inactivation credits, right? Or similarly, you can use it to treat the spent media, right? So we've developed also not just a liquid or our plasma water reactor, we have a plasma solids reactor. So looking to regenerate activated carbon real time, or for example, using some type of solvent to rinse it off and then destroy that solvent. Similarly, in the RO-based treatment train, you have advanced oxidation on the back end. As I mentioned, plasma technologies already exist there, but if you're directly injecting plasma in there, you should get enhanced destruction. So if we replace that, we should be able to get additional credits, or in this case, address the concentrate stream as others have mentioned. And so, summary, what we found is that plasma can operate regardless of the background matrix to achieve whatever metrics you're looking for. We believe that some of the best applications include decentralized water treatment, where you're off the grid and you know, you can couple this, for example, our pilot unit, we're trying to hook up to solar panels so that it can be fully off the grid. For example, this landfill is in the middle of nowhere and struggles to get power and sometimes loses it. So we're trying to create these remote and resilient units that can operate on their own. And then ultimately, we're putting our analytical tools in the trailer as well so that we can bring it there and analyze these things on site. But at the end of the day, what we believe at Purified is that ultimately we can online monitor these things and real-time treat them. So, you know, we'd like to thank the different agencies that work with us, state environmental agencies, you know, thank you for paying your taxes so we can get some government grants. And then, you know, this is some of our team members here. You know, we've expanded since this slide was made. But one thing I just wanted to touch on is that really what we're focused on is the addressing sustainability and being, you know, focusing on environmental justice. So for example, with our water or with our analytical capabilities, we're trying to team up with marginalized communities to provide them with free analysis. So for example, historically, tribal nations are located, you know, less than, I don't want to lie to you, I forget the exact numbers, but majority of them are within like a 10-mile or 15-mile radius of a Department of the Defense site, which is notoriously known for PFAS pollution. So if we can help them identify sources and then ultimately destroy them, that's a win-win for everybody. And so as you know, we want to break the contamination cycle, and then this is that model that we use to determine who we should be able to help out. And so with that, you know, we want to be able to deploy more pilots and partner with those in need. And so if you want to team up on a project, let me know. Thanks.
Thanks. Okay. Next up is Eric.
Tight. All right, good morning, everybody. It's good to be here today. Thank you to our host and our sponsors for today's session. It's an honor to be speaking to the crowd. Want to reiterate something that Salman said earlier in today's session, which is, while we're all speaking about destruction technologies here in this session this morning, and we all might seem like competitors, we all are truly kind of team members in this space. we're all going to have kind of a lane in which we're playing in. PFAS is such a diverse problem that there's going to be kind of room for everybody here. And we all want to see PFAS brought to end of life. So that is our goal here at Revive. It's bringing PFAS to the end of its life, closing that destruction loop. And we're going to talk a little bit here this morning about two specific ways in which we do that. So we're going to talk about how we approach kind of those concentrated applications. So for example, those AFFF materials that have been brought up previously. Then we're also going to talk a little bit about how we approach those kind of dilute recurring streams, those groundwaters, those landfill leachates, industrial wastewaters. A little bit of background about Revive Environmental. We are a spin out of Battelle Memorial Institute out of Columbus, Ohio. Battelle is the group that originally developed this technology a couple of decades ago and repurposed it several years back for PFAS. So something to keep in mind as we talk over the next few minutes, the PFAS annihilator, which is that SQO technology that we're operating, works for all organic material. It's not just for PFAS specifically, it will work for all organics. And so they kind of identified this issue that PFAS was coming about several years ago and said, hey, we've got this system that really works well for organics. And they spun out Revive Environmental to commercialize and provide this technology to the market. So you'll see there at the bottom of the screen, the key industries and projects where we're working. We're going to focus on those left two most groups today. So AFFF material and that landfill leachate bucket, but know that we're doing more work than just those two specifically. Rosa had brought up the EPA compounds that were referenced last week, and they made some commentary about updated drinking water requirements. At the time I built this slide, this is what the MCLs look like. They have since changed or potentially will change, and we could potentially see even more changes. So one thing to highlight is PFAS is an ever-evolving landscape. We used to call these compounds PFCs years ago. Now they're called PFAS. The MCLs have been adjusted and changed. Timelines have changed. So the scope in which PFAS needs to be treated is constantly changing. So it requires a flexible treatment technology that's also going to provide a permanent and complete destruction loop. So there's not potential rub with upcoming changes with regulation or requirements for what that treatment train might have been originally designed for. Other thing to note here is whenever we refer to destruction today, this is what we're using as our anchoring point. So whenever we define destruction at Revive, we're using this drinking water standard as that guiding principle. So if we say we destroyed a material, we're talking about destroying whatever that base material was down to the standards that you see there on the screen. Quick summary of SQO and what it is. So supercritical water oxidation, or SQO as we'll shorten it to, is essentially a high temperature and pressure process in the presence of excess oxygen. So what we're doing is we're taking in liquid material, emphasis on liquid. We do not do solid material. We're a liquid focused company. We'll take in liquid material into reactor system, elevate the temperature up to 500, 600 degrees Celsius, pressure up to 3,400 PSI, and then apply an oxidant. So in our case, we're using hydrogen peroxide. Under those conditions, that breaks that carbon-fluorine bond mentioned by Rosa earlier this morning and mineralizes that PFAS out. And on the back end, you get three primary components. You're going to get a majority of clean water, again, defined as meeting that drinking water standard. You're going to get a salt brine, non-hazardous, non-PFAS containing liquid industrial byproduct, and a small amount of emissions as well. What do these systems actually look like? So we have 7 of these systems fleet-wide. The our facility in Columbus, Ohio. So we've got 3 of these systems put together in under one roof. A couple of things that you're going to notice from these systems and what this facility looks like. Number one, these are 20-foot shipping container systems. So while these are situated at a fixed destruction facility, they can be taken for an on-site deployment, a pilot, or some kind of demonstration project where we might not be able to do destruction at our facility and we need to go and meet the customer, meet that demand there on site. The other advantage of this process is this allows us that operational flexibility to kind of push and pull that production capacity as we need it. So we've got another facility in Grand Rapids, Michigan, where we do destruction as well. And depending on market need or project need, we can take and kind of mix and match these annihilator systems to support these projects. These systems are all identical in design and operate in the same way, but the way that we've tweaked them and engineered them over the years gives us that ability to process different materials differently. EPA put out a guidance document last year commenting on PFAS disposal methods. And while they didn't necessarily give specific commentary on any of the technologies you're going to hear today, what they did do is they looped us all into a big bucket and said, hey, if you're willing to consider, you want to consider a PFAS quote unquote destruction technology, here's what you should be looking for. There's six criteria there. We're not going to go through all of them for the sake of time, but I'll call out a couple that are important to Revive and how we're a little bit different than some others. Number one, the technology readiness. So we would consider our readiness level at a technology level of 9. We've got 2 fixed facilities in the United States operating 7 different SQO systems at those facilities. The other requirement that really separates and differentiates us is the efficacy requirement. So that 4th one down there on the list. So again, SQO is not a destroyer of the specific group of PFAS compound. It's not going to convert some compounds to others. SQO is going to destroy any of those organic materials that enter that process. So we achieve what's called a breadth and depth of destruction, where we're taking that entire PFAS umbrella, destroying it down to low or non-detected levels of PFAS. We'll show some data of what that looks like here in a second. The other key differentiator that we're working through with our customers is that down there on the left-hand side on the bottom, we can do batch by batch confirmation of destruction of all of these projects. So if we get material in, we could have a warehouse with a queue of some landfill leachate concentrate, some AFFF material, maybe some concentrated groundwater. We can batch those specific projects individually and provide analytical verification on each of those specific projects to prove out destruction. What that does is it allows our customers to have that liability relief long-term of those materials, because what we're doing is we're destroying that material, we get that analytical verification, and then we will discharge that treated water through a permanent discharge point. So we're not sending that material back out to a customer site. We are taking it and we're discharging it to the local POTW under a permitted process. Look at some data and case studies here. So we'll talk about, again, AFFF here at first, and then we'll transition over into some of those more dilute streams. So we'll talk about some material we pulled from projects like the AFFF state take-back programs we've executed recently. This particular material at the top, if you notice, there's a couple of letters here. It stands for AR. That's an alcohol-resistant AFFF. Essentially what that means, it's a highly durable material, tenacious and tough to destroy. And what we've done here is destroyed this material through one pass in the annihilator system. You get the data that you see there in front of you. The important thing to know, this is representative of data that would be pre-polishing. We are not doing polishing on PFAS specifically. We do have on the back end of our systems a filtration system to help meet some of those discharge specs, but it is not doing the heavy lifting in terms of PFAS treatment. So this data would be representative of destruction data before it would enter any kind of filter. A couple of things you'll notice. Number one, we've highlighted those EPA drinking water standards that, again, are now already a little bit dated, but you'll see, some of those long chain compounds, PFOA, PFOS, being taken from a couple thousand parts per trillion down to 1 part per trillion or below. Some of those smaller, shorter chain compounds, PFBS, in the 4,000 to 5,000 parts per trillion being brought down below 1 part per trillion. The other compound we'll point out here, we've got PFHXA, for example, 3rd one down here on the list. We're dealing with materials that are in the % level of PFAS, meaning it's part of the active ingredient that make these materials work. There's a lot of PFAS in them. So we're seeing hundreds of millions of parts per trillion of different PFAS compounds that come in these formulations. And with a single pass through this process, we're getting down to 3 part per trillion. Talk a little bit about how we view destruction with SQO in terms of a mass balance or a TOF mass balance. So this technology in terms of POF or TOF mass balance is still developing. So one thing that we'll kind of preface this with is there's still some data gaps there and some analytical gaps when it comes to these mass balances. But there have been mass balances performed and performed recently on this process. So we're going to highlight a particular case study here where a study was done on a very similar material to what we just talked about earlier, an alcohol-resistant AFFF. The key findings here, number one, they observed a significant reduction in total organic fluorine from the influent to the effluent. So a very small percentage of that effluent material was observed to be organic fluorine. The organic fluorine, again, that would represent potentially that PFAS component. So greater than 99.9% of that effluent contained an organic fluorine. The specific number there is here on this right-hand side, the 26 parts per trillion of total organic fluorine. The other key finding here is on the vapor phase, very trace amounts of total organic fluorine observed in the study. So 0.04 parts per trillion of total organic fluorine in that phase, essentially negligible. It's hard to even measure down to that point. There are more studies being done with TOF mass balances. This is a developing field. Ideally, this would be the way to kind of do additional PFAS measurement because, the way that we're typically measuring PFAS destruction, kind of as a group in an industry is you're usually doing targeted analysis because you can see very clearly what some of those compounds are. TOF gets that entire picture. However, the data gap here being is the alignment between the influent and effluent material is still not quite there. We observed 140% of the fluorine in the effluent as compared to the influent, essentially meaning we didn't measure enough fluorine on the influent. There was some portion missing. So again, this is still an ongoing field of study, and we hope that this analytical technology develops. All right, we'll close out here with what we're doing with kind of those dilute recurring streams, again, landfill leachate. So we'll use that as the example today, but this could also be applied to applications like an affected groundwater or an industrial wastewater site. So we have two models here at Revive. One model is a complete turnkey solution, which would be represented by this truck here that you see there on the screen. That would be hauling that raw water to one of our service facilities where we would provide both these steps that we're going to talk about, separation and destruction at our site, or, and this is almost always the most economical approach, applying that separation technology at the customer site so you're not hauling all of that water. You just have to haul that concentrate after that process has been completed. We're technology agnostic in terms of how we do the separation. So there were some separation technologies talked about earlier in today's presentation. We're going to talk about foam fractionation here in this particular case study, but we've worked with reverse osmosis concentrate. We've worked with adsorption media concentrates, solvents that have, wiped the PFAS off of that particular adsorption media. So where we've actually taken this and brought it to a site, this was a landfill out in the Midwest United States that needed to meet a PFAS discharge permit targeted on PFOS and PFOA. So they needed to get down to 8 parts per trillion on PFOS, 20 parts per trillion on PFOA. Those are pretty tight discharge permits, and that's because they're sending to a wastewater treatment plant that discharges the surface water. So they're being held to a tight standard. They're also needing to treat a combination of groundwater and landfill leachate with 65 plus million gallons per year. So you've got a lot of volume that needs to be treated, a complex matrix due to the fact that it's a hybrid of different water streams, and you've also got to reach a tight discharge permit. In this particular project, what we did was apply the ammonia SAF systems to separate that PFAS out, and that was done very efficiently. So we got up to 90,000 times concentration or separation of that PFAS. Way to contextualize that, if we treat 1 million gallons of water, we got 14 gallons of PFAS or PFAS concentrate as a waste stream to deal with. So you can see how that makes that process much more economical, where you're not destroying or having to treat and transport all of that material. When we got that foam concentrate and took that to our site in Columbus, Ohio, and did destruction on that material, you could see the data there on the right-hand side That foam concentrate is represented there in that concentrate column. That clean effluent represents the effluent from processing that material. Again, we saw what we kind of expected, very highly concentrated PFOS, PFOA compounds, some of those longer chains, and there were some other compounds there as well in relatively high concentration. But through one pass of the annihilator, we saw significant levels of reduction to PFOS. This is all in parts per trillion, so we saw, less than 1 ppt in PFOS and PFOA, well below that drinking water standard, beyond an order of magnitude. So to sum up, again, the PFAS annihilator is going to provide that strong depth and breadth of destruction on concentrated material. It's not going to provide a waste stream or generate a significant waste stream as part of that process. It's going to pair well with some of those other technologies like a foam fractionation or reverse osmosis system to treat some of those maybe dilute recurring streams. And this is a technology group that we're applying out in the market today. Thank you.
Okay. Sarah.
Thanks, Tom. Hello, everyone. Again, I'm Sarah Meyer from Inspired Solutions. I'm the Chief Operating Officer. And, oops. Okay, just getting oriented here. I'm going to talk with you about our UV-based destruction technology, photoactivated reductive defluorination. We are a women-owned and women-led company located in Lansing, Michigan. We opened our doors in 2021, and all we do is PFAS destruction. We did proof of concept on hundreds of benchtop samples of this chemistry and designed and built the reactor that I'll show you how that works. We call it the PFASigator. And today we are here today to talk with you about our technology. I'm going to jump right in and talk about how our technology works. I'm really happy that this panel is all PFAS destruction, really emphasizes the fact that these technologies stop the cycle of collecting PFAS, moving it somewhere else, where there's a risk of it being re-released into the environment. By destroying, I feel like I'm electrocharged here. By destroying the PFAS, we're breaking that cycle. And photoactivated reductive defluorination, or PRD as we call it, is one of these destructive technologies. It breaks the cycle, transforming PFAS into non-toxic discharge. This is how PRD works. If you look at the left-hand panel of this cartoon and you imagine that the blue dots are PFAS molecules in water, we add 2 liquid reagents to that water. The first one forms this micelle structure that you see in the center panel, and the PFAS align around the outside of that micelle. The second reagent clings to the outside of that structure. Now we call this a reactive cage because we have both the PFAS and the reagents clinging together in this package. When we shine a UV light onto that solution, it catalyzes the reaction that breaks the carbon-fluorine bonds of the PFAS. The final byproducts of that process are fluoride, water, and simple carbon molecules like formic and acetic acid. I'm not done with that slide. This reaction happens at atmospheric temperature and pressure. And also with the production of that fluoride ion, we're using that in our technology to actually monitor in real time the destruction of PFAS with our equipment. So we have an onboard ion selective electrode for fluoride on the machine that watches the accumulation of fluoride as the PFAS are mineralized in solution. This chemistry has won an award from both EPA and the Department of Defense for meeting their criteria for PFAS destruction and energy efficiency. This is a graph of some real-world results of our PRD destruction process. On the y-axis is total PFAS concentration in log scale, and the x-axis are the 6 formerly regulated MCL PFAS. And then the different colored bars as concentration of those PFAS with different treatment doses, different UV doses, or time of treatment. So if you just look at the PFOA, PFOS clusters there, you can see initial concentrations were over 1 part per million. And with treatment time, those concentrations decreased to tens and hundreds of PPT. At the time that we turned the UV lamp off here, you can see all of those curves for the different PFAS follow the same trend. If we left the lamp on, all of these PFAS would be non-detect. And obviously this is, you can see the effect of the destruction technology on these 6 PFAS, but all PFAS in solution are being affected the same way. Their concentrations are decreasing over time, and with increased UV dose, they would all become non-detect. This is a surface water sample, actually, that was concentrated by foam fractionation prior to us destroying the PFAS. So how do we take that chemistry and translate it into a commercial scale reactor for real world deployment? We built the PFASigator to do just that. We are at TRL level 8 to 9 right now. We have completed the technology and qualified it with multiple field demonstrations. At the end of last year, we sold our first unit. Our model is to sell equipment to you to operate at your own site. We are negotiating contracts for additional sale of PFASigators now. And for the next 12 months, we have multiple field pilots lined up for treating landfill leachate, RO concentrate, groundwaters, surface waters, and AFFF. Here is the PFASigator, and I'll show you the process flow here. It's an automated machine. The influent comes into the PFASigator. This would be a concentrated concentrated PFAS solution. The reagents are mixed in, and then that batch is run past the UV lamps for on the order of hours. When the treatment targets are met, and we measure that by the treatment time, wow, this is kind of auto-advancing on me here. Sorry about that. We would determine the treatment time based on a treatability test in the lab, and we're also watching the production of the fluoride ion in the field, so we know when we're meeting the treatment targets, we can confirm that that's happening, and then the batch is automatically discharged. So in terms of monitoring and control of the PFASigator, again, the automated influent and effluent processes, the reagents are dosed automatically. We have the real-time fluoride measurement going on with the onboard ion selective electrode. And then the whole system can be monitored remotely from a dashboard on a computer in your control center. It also sends alerts to your phone if you're looking at system updates and say level of reagents, et cetera. So now I'm going to show you a case study where we applied the PFASigator in the field. And we've talked here about how concentration is important for the efficiency of PFAS destruction. That is true for our UV-based system also. Our system works most efficiently if you concentrate ahead of time, because for each order of magnitude that you destroy PFAS, you're spending the same amount of energy or cost. So we like to operate the PFASigator at high concentrations, destroy 1 or 2 orders of magnitude of the PFAS, and then recirculate the remaining PFAS back for reconcentration. And I'll show you how that works. We start with a contaminated groundwater source. That groundwater flows into a separation and concentration unit. Let's say foam fractionation does that. The foam fractionation unit removes the PFAS and discharges the remaining water. That would be your permitted discharge. That concentrate now comes into the PFASigator, where we destroy 1 or 2 orders of magnitude of the PFAS, and the remaining PFAS is recirculated for reconcentration again. So this destruction loop continues on the waste coming out of the contaminated groundwater as it flows through the separation and concentration unit. This is a photo of that recirculating process flow happening in the field. This is at an industrial facility in Michigan. On the left-hand side of the screen are totes of groundwater. They had a historic release underneath their plant. So we were pumping groundwater into the facility, and that groundwater first went back to the foam fractionation unit at the back of the room there. That was removing PFAS and concentrating it into a foam. When that foam collapsed, it was sent to the PFASigator here on the right side of the room. We destroyed for this pilot study between 87 and over 99% of the PFAS in those batches, and then returned the remaining PFAS back to the totes on the left-hand side to get mixed back in for reconcentration. Good timing on that. Here's some data from that pilot test. PFOS concentration on the y-axis, this is what they were being regulated for at that facility. Batches on the x-axis. Dark blue bar is concentration before treatment. Orange is concentration after treatment. And then the teal dots is percent destruction for each batch. So we were achieving over 99% destruction there. This is that recirculating process flow again, showing the volumes and concentrations for that field pilot. And then I'm overlaying here the cost per gallon that we calculated for this pilot project. On the left, you see less than half a cent per gallon of system influent, that being the groundwater. And on the right, you see $3.84 per gallon of concentrate. It's one or the other. $3.84 per gallon of concentrate. That includes both the CapEx for the machine and the OpEx to operate the machine, including the energy cost. Generally, we say costs per gallon of concentrate treated with the PFASigator ranges from $2 to $7 per gallon. And the difference is the matrix that the destruction is happening in. For a cleaner matrix like groundwater, the cost will be lower. For a more complex matrix like landfill leachate, the cost will likely be higher. For very high flow situations like municipal water, wastewater, we have been working with regenerable media that can handle very high million gallons a day plus filtration to remove the PFAS. Then that media sorbent can be regenerated. The PFAS is washed off of that media, and the PFASigator takes the concentrate, that regenerant concentrate, for destruction. Similarly with the foam fractionation, the remaining PFAS after destruction would be recirculated for refiltration. So the recirculating process flow, but at a much higher flow rate. A few additional notes on capacity and scalability. Without knowing anything else about your situation, we generally say one PFASigator can treat 200 gallons of concentrate per day. For higher flows, these are modular units, so you could deploy multiple PFASigators at the same location to treat the same stream. For very large waste streams, like the municipal flows, we can work with regenerable sorbents, treating the concentrate that's regenerated from those materials. And then lastly, actual capacity of the PFASigator is site specific. So we would run a treatability test to understand exactly what the destruction rate is in your matrix. Key challenges and breakthroughs for us. Just over the lifetime of our company and our technology development, we discovered that we could, because we're operating at atmospheric conditions, we can actually measure the production of fluoride ion as the PFAS are broken up. So we have that measurement happening in the technology, and we can see that happening in real time. We can confirm the destruction is happening. Low UV transmissivity. There was a question at first whether that was going to be an issue for waste streams like landfill leachate that could sometimes look like espresso. This turns out to not be an issue for the PFASigator. I'm technologically challenged today. Because of two things: the reactive cage that is formed in the chemical process, and then also the batch reactor that the PFASigator is. So each of those packets has a chance to run closely past the UV lamp for destruction to occur. So we're seeing good reaction rates, even down to less than 1% transmissivity, or even down to 0.1% transmissivity. UV lamp fouling in early runs of the actual unit in the field, we were seeing that the lamp could be fouled with a film of reagents. We have since changed the lamp over to mechanical wipers, and also we're pre-mixing the reagents and the test solutions, and we've been able to avoid the lamp fouling. And maybe hopefully you'll get a copy of the slides and you can see the rest of the items there. Thanks, Tom.
Yeah, sorry about the advancing. I don't know what's gone on with the program here, but you know.
Unplug the clicker.
Is it the clicker doing it?
I don't know.
Here. We'll
Yeah.
unplug the correct clicker, so you need to use the forward and back. Last up.
Okay, thanks, Tom, for organizing. Thanks, Stefan and COE for both support to DMAX Plasma and organizing this session. I'm excited to be here. So first, the leadership team of DMAX Plasma, myself and Selma, who's somewhere here in the audience. We're both faculty members at Clarkson University. We discovered, I guess about 15 years ago now, that plasma water treatment can break the carbon-fluorine bond, much to our surprise. We started DMAX in 2014. Fortunately, not long after that, we met Ken Camarco, our CEO. He was on the board of trustees at Clarkson, has extensive background in water treatment. And since Selma and I still have full-time jobs, he's largely running the show now. So just some background on DMAX. We've had about 30 successful field trials. I'll talk some about those. We say we're TRL at 7+. We've treated about more than 10,000 gallons in our field trials. And unlike the other technologies you've heard about today, we're very flexible in the initial concentrations. We can treat low concentration groundwater at hundreds or thousands of nanograms per liter, and effectively treat very high concentration streams by changing our contact times. Someone already told you what plasma is all about, so I can skip that slide. So our technology is based on bubbling gases on the right-hand side. I guess, I don't know if the pointer is gonna work. So we bubble gas through the water column. concentrate the PFAS at the interface where we generate plasma, as shown in this slide. So we're separating the PFAS from the water streams, so co-contaminants, things like that, don't interfere with our process. So as I mentioned, we're quite flexible. We can work from raw water, low concentration streams to very high concentrations. We've worked, as I mentioned, with groundwater, leachates, industrial wastewater from semiconductor manufacturing, AFFF foams, stormwater. More recently, we've been working with some soil washing solutions. Here's a picture of one unit we've delivered to an industrial client. The plasma generating units on the left. Here, the reactor is in this box, influent, effluent tank. And here's a picture of the plasma being generated on the surface of the water. Hopefully this video will work. So we charge capacitors, discharge them about 60 times per second right at the surface of the water and generate the plasma. Typically, we work with multiple reactors in series because PFAS is being quite sticky. If you try to treat from micrograms per liter down to discharge limits in one reactor, you get desorption problems. So we treat in series, high concentration, middle concentration, pulsing reactor. I show 3 here. Our trailers actually have 5 reactors in series. For higher concentrations, then we short circuit this flow through design and do sequential batch treatment. So we treat a high concentration in this reactor for whatever time is required, typically maybe hours, switch it to the next reactor, keep moving it down the chain till we reach the limits that we want. Done quite a bit of discussion on cost and throughput. Fortunately, the format doesn't work too well here, but it doesn't matter. So our trailers are typically around 20 gallons per minute. If you want higher flow rates, then you can put multiple trailers or multiple treatments in series. And as concentration increases, the flow rate goes down because you have to treat it longer, right? Makes sense. Cost for direct groundwater treatment, we're in pennies per gallon cost. And as treatment time increases, costs go up, obviously. Right, so from pennies per gallon to dollars per gallon, depending on the matrix. So what are we doing now? We're working to increase our inventory base, more treatment trailers, increase capacity, so make the reactors more efficient. Ongoing product development, as all of us in the room are working on, trying to improve our technology and increase opportunities. Just one kind of generic slide here, kind of the orange is what we typically do with the plasma process. If we combine it with some other processes we're working on, we can, the blue is data. The orange is what we're working on when we combine treatment technologies together, which we're calling Plasma Plus. So let me quickly wrap up so we have some time for questions. Trailers, one of our trailers in the field, 5 reactors in a typical trailer. So we've shown it works for a wide range of matrices. We can scale to the needs of the client, cost effective, and as someone pointed out, plasma technology is quite sustainable. Little limited additives required and energy efficient. So quickly ran through that to give hopefully 15 minutes or so for questions.
Thank you. You guys can all come up, stand along the edge here, and I guess if we have questions, we can use some time now to answer questions. If you ask a question, maybe I'll hand off the microphone to you, and that way the remote viewers can hear. Maybe everybody just wants to go to lunch. But okay. Let's see.
Great presentations and very impressive technologies. So the key question here is, and the key destructive technologies or complete destruction. My question is on degradation byproducts. Many of these and all of these technologies are producing fragments of PFAS. And the idea is you have something that is completely non-toxic, but is it true? Have you looked at things like TFA, for example? Thank you.
I'll start here, pass it down.
Yeah, great question. We have looked at TFA. Unfortunately, it's extremely difficult to analyze just because it's everywhere. So I can't say with confidence, conclusive evidence just because our results, every time we run the analysis, you can see like significant changes in the results. But typically we'll use PFBA as our indicator compound to show that those are, they should increase in concentration, then ultimately decay away, and then that's when we feel pretty confident. And typically we work in concentrations that are extremely low, so then we can't use, for example, like fluoride, like the way Sarah uses the fluoride ion selective electrode, for example. Like we can't use that, so we typically try to measure for PFBA.
What he said. We do see, especially for high concentration streams that we're treating, you'll see during a timed study where you take samples along the way, you'll see a rise in PFBA, PFBS. We don't routinely measure TFA. I'm sure that goes along as well. So you've got to run long enough to back those back down, or use like a polishing ion exchange resin or GAC or something afterwards to kind of clean up any of that you didn't get all the way back down.
Yeah, we have not seen conversion of compounds with the SQO process from maybe long chain to short chain or one compound to another. That's supported by the TOF mass balance that has been performed recently. The TFA analytical is still developing. I would echo some of the same sentiments Selman stated, but certainly we're looking for other compounds than just maybe the popular EPA 1630-340.
What they said, plus ours is a reductive pathway, which is different, I think, from everybody else here. And it avoids oxidizing something in the water to a less desirable form. So we know that we're avoiding some of those potential toxic byproducts because of that. We have done work for the Department of Defense where they've required that we actually sample our discharge for specific things that they feel they want to know is in the water. But similarly, we haven't looked for everything under the sun in our discharge. So it is evolving.
Maybe just a quick comment. When Selma and I started, it was C8s, all anyone cared about. And as time goes on, it's shorter, and now ultra short chains are certainly on people's radar. Plasma can remove them. It takes longer, so you're farther up that cost curve. So it's a trade-off to use plasma to do that, to use activated carbon polishing. There's many options to get at those.
So as I'm handing off the mic, I'll just summarize what I think I heard was that generally there is a need for some sort of polishing step for a lot of these destruct technologies.
Hi, I'm Dave Knable, retired National Program Leader for the USDA Agricultural Research Service. Great presentations on really important technologies. And I've got a challenge for you. I mentioned USDA farmers are trying to figure out how to address PFAS in their irrigation waters, their groundwater, cost prohibitive. And so you might not have the answer to this, but are any of you thinking about scaling down to where this could be at the farm level of a technology? Or I realize I've heard a lot about concentration and shipping. Just want to put that out as a challenge. And then you can report on that at a workshop that we'll be co-sponsoring with the University of Maine in the fall of 2026. Industry will be invited, number of stakeholders. My name is in the program on the back of the first page. Just put a dot between my first and last name and at usda.gov. But is anybody looking at that small scale economical destruction technologies. I didn't really hear it, but any thoughts on that?
We'll start at the other end and work our way back. So.
I can't say we have a demonstration going on in about a month and a half, looking at stormwater runoff from an airport, which is kind of low concentration, intermittent flow that Dave was talking about.
I'll be honest, we're so focused on getting our optimized PFASigator out and functioning well and selling in the world that we're not ready yet to go to a smaller scale residential style unit. But that is one reason that we've looked at and worked with these regenerable sorbents that are out there, and they are commercially available to be able to destroy the PFAS in the regenerant solution that they create when they wash the PFAS off of those. Those are easy to operate, easier to install, relatively affordable, and then the destruction happens on the back end of their process.
Yeah, we don't envision SQUO being applied at such a scale. The systems that we provide this as a service to our customers, and there's a few reasons for that, but one of them, it's technically difficult to operate the system. So we don't envision scaling down to that point. But I think back to what we talked about early in this presentation, there's going to be, applications that apply more to one of these groups of technologies than others. So that maybe not be the fit for SQUO, but might be a better fit for some of these others here.
Yeah, it's interesting to think about what you said. We're not directly putting our electrochemical oxidation to work in a stream like that, but we are, with another water treatment company, building a pilot system which includes the electrochemical oxidation upstream and then a combination of either resin or GAC downstream to take on these lower starting concentration types of projects, and that could be interesting. That might be an application for that.
Yeah, we've been looking at agricultural applications specifically, especially with the concern, like we've been working with Maine's Department Environmental Protection, specifically with the concern with biosolids. So anybody will use an excuse to get rid of their biosolids. We're trying to show that we can not only destroy the PFAS, but potentially enhance like nutrient gains and enhance pathogen inactivation.
Okay.
Hi, this is Don. I have a different kind of challenge for you, which is suppose you have a client who's a semiconductor manufacturer and they use PFAS and they have a fairly large volume, million-gallon day levels. How would you address that? And if you can talk about costs, I know Sarah and Tom, you talked about costs, include that. Thank you.
I'm going to start in the middle this time, and then we'll go that way and then that way. So.
Yeah, in terms of cost, so you mentioned the high volume application, millions of gallons. Was it per day or per year? Per day. Yeah. So on that scale, I think no matter who you're going to talk to here, that separation piece is going to be critical. To destroy at that scale, you're going to have some efficiency driving towards a higher concentration material, stripping it out of that high volume of water. So, we have a few models in which that could be successful. Our GAC Renew technology specifically uses granular activated carbon to remove the PFAS out of such a stream and then treat that solvent that would be used to wash that PFAS off of the GAC. So you're going to look at a price point there somewhere in the neighborhood of what you typically see with thermal reactivation, which is going to be on the $2 a pound range.
Yes. As Eric said, a separation technology for that size waste stream is what we envision for semiconductors. Beyond that, we actually have tested TARC solutions that semiconductor wafer lines use, and also some components of their wastewater And we're doing some work with a semiconductor now just to understand how our technology applies actually to that waste stream. That's kind of the first step. And then determining how to concentrate that waste stream and apply the technology would be the second step.
You know, we've been working with semiconductor manufacturers, similar to what Sarah just mentioned, and we were trying to move upstream to the source of the fluorinated surfactants, which are hundreds of gallons per day. So we can deal with those high concentration streams before they get mixed with the high flow rates. I think that's really the best solution for those kind of manufacturing sites.
Thanks. Yeah, similar, right? If you can move upstream to the parts of the fab that are actually using the PFAS and attack those rinse waters before they go into the general wastewater, like in an end-of-pipe treatment plant, that's one thing. And then depending on what you have to treat for, foam fractionation may not be the answer for pre-concentration because it doesn't do as well on things like TFA or other short chain and ultra short chain compounds. So a membrane technology for pre-concentration is probably the best thing to look at. So shrink the stream by going upstream, finding the highly contaminated parts of the fab wastewater profile, and then membrane concentration. That's what we see as the best way to attack the semiconductor wastewater problems.
Agree with all the above. The only thing I'll comment on is a lot of these fabs have already treatment trains installed, so figuring out where to plug in the destruction technology is pretty critical.
Yeah, and I'll add to that. So the way that these semiconductor fabs are built, there are multiple steps in the process. They're only using PFAS compounds in certain steps. And, as you look at those fabs being built, you can actually isolate the drain systems for those particular parts that are focused on using the PFAS compounds. So you don't, in the end, have to end up with a super large waste stream with a more dilute PFAS concentration. You can actually, like they said, attack it at the source, gather at the source where it is more concentrated, apply maybe some concentration, maybe membrane based, and then destruct from there. So I think that takes us to noon. Thank you, everybody. Thank you to our speakers as well.